Alright, so we're back with the fundamental theorem of calculus. This time we're going to talk about the second part, and it actually looks very much like the first part, and the first thing we should talk about is some of the similarities. So, in the previous video we talked about the fundamental theorem of calculus, the first part, right? And this is what we had here in talking about how the accumulation or the area function is an antiderivative for f. So the profound thing about this theorem is it's really telling you that the area and differentiation are actually opposite operations. So you can see if you begin with a function like f and you integrate it, right, you find the area and then you differentiate it, then not much has happened. So you can see that the function here pretty much comes back. So it's really telling you about the inverse nature of the area under the curve and then also the rate of change. So the big thing I'll show now is what the second fundamental theorem of calculus looks like. And so I won't talk about what it means in the beginning, we'll just talk about how it's similar. Okay, so in a minute we'll talk about the meaning behind this. So this is the second fundamental theorem of calculus. So remember our notation here that capital F is an antiderivative for little f. So we want to remember this stuff here. Right, so capital F is an antiderivative for little f. So you can think of little f here as being capital F prime. So this statement here has a similarity to the first fundamental theorem, mainly because you start off with a function capital F and you find the derivative and then you integrate it. And what ends up happening is you get capital F back, right? Except this is calculated at the endpoints B and A. So this is really showing differentiation first followed by integration. This one is showing integration followed by differentiation. So that's why there are two parts to the fundamental theorem of calculus. They both illustrate how the area and the rate of change are opposite functions, but each statement illustrates that by reversing the operation. So the first thing we should talk about is what does this statement here mean? I'll push this here and we'll just unravel it and talk about it. Alright, and the first thing I had mentioned here is that capital F is an antiderivative for little f. So typically the way you will see this written, you'll see integration from a to b capital F prime. I actually like this form better. Right, it takes on this form. Because this way you don't have to really know the relationship between little f and capital F. It's just saying we're trying to find the area underneath this curve starting from A to B, and it ends up what we have to do is three things pretty much. So you have to first look at f prime, find the antiderivative. So notice there are no primes or derivatives over here, so you have to find the antiderivative f. The second thing you have to do is to calculate at the endpoints A and B. So you can see that occurs here, A and B. And then the third thing is to simply subtract. So most students like the second fundamental theorem of calculus a little bit more because this is the one that allows you to compute the area underneath the curve. So when we try to understand the fundamental theorem, it's really telling you this. So you could have some function here. So this little f is the same as the f here. And so you bound this function on the left at A, on the right at B. And remember, it's been quite some time we're trying to talk about how do you find the area underneath the curve. This is exactly how you do it. So you have to find an antiderivative of this function, right? That would be capital F. And then once you find that antiderivative, all you have to do is subtract at the endpoints, right? F of B minus F of A. So this really makes light work of finding the area underneath the curve. We don't have to talk about approximation anymore, and it's a very, very efficient way to calculate area. So we should look at an example here. Maybe a couple, and then just relate it to some of the older things that we've talked about. So a couple of problems here. Problem A here is saying let's integrate from 1 to 2, and this is a very simple function, right? Y equals x. So we can think about this graphically, of course, but I'm going to try to use the second fundamental theorem of calculus to do this. So for problem A, I'm going to write this down, integrate from 1 to 2, x dx. Okay, and I'm going to put this up here just so we can see it again. So the first thing we want to do is to find the antiderivative of little f. So this is going back quite some time, but when you think about x, we concentrate on that. X to the first power, the antiderivative here, we're going to upgrade the power by 1 and then divide by that. Now what is typical here is we need to plug in the numbers 2 and 1, so the common notation is a vertical line like this, and we put a 2 and a 1, and this is telling us we're about to substitute the 2 and the 1 and then to finish off the calculation. So if you put a 2 in here, you get 2 squared over 2. Then subtract off and put the 1 in, 1 squared over 2. So just to emphasize here, this is f of b, right, minus, and this is f of a. That's all there is to the fundamental theorem of calculus. Find the antiderivative and subtract at the endpoints. Naturally, we have to have the function to be continuous on this window from 1 to 2, so there are assumptions, but most of these problems are well posed. So 4 over 2 minus 1 over 2, so this answer ends up being 1 1/2, right, 3/2. So this might not seem like a big deal, right, like a pretty easy problem to do. And in fact, I think we looked at this one probably in an earlier video. If you think about the function y equals x, right, that's a nice simple function to graph. So you cut it off at 1 and at 2. So we put these vertical lines at 1 and at 2. And when we calculated this, you could draw a little line here, just like that. And so you have the area of a square. We have 1 there and 1/2. So you end up with 1.5. So this example here happens to be, the geometric figure you get happens to be very, very convenient. And you can calculate it via a picture. But the beauty and strength of the fundamental theorem of calculus is notice that you get the same answer here without a picture and with minimal calculation, right? So you find the antiderivative and simply subtract, and you have this answer there. Alright, so let's take a look at B here. So we're going to integrate from 1 to e, that's about 2.7, 1 over x dx. Right, this problem I feel is not going to be as straightforward, right? Especially in terms of trying to do it with geometry. So the first thing we'll do via the fundamental theorem, we'll double check if this function is continuous here and it has no problems. So the antiderivative of 1 over x, you might remember, is the log function. This is ln of x. Like that. So that's our pure antiderivative, and we need to plug in these numbers. So we have e and 1. So natural log e minus natural log 1. So we get ln e minus ln 1. And so remember, the natural log is just saying find the exponent on e that gives you this value. So the natural log of 1 is nothing, right? That's 0. The natural log of e, the exponent on e that gives you e is 1. So this gives you your exact area, right, in square units. So again, just look at the picture, and we can see why the fundamental theorem is such a potent theorem. So if you look at the graph of this function, 1 over x, right, it's the area here, and it's going to be the area from 1 to e. So we could see 1 is here and around 2.7 or so. So we're going to calculate this area that we see in orange. So unlike the previous problem, this is not a convenient geometric shape. There's no simple way to calculate this exact area because of the irregularity of the shape. But the fundamental theorem of calculus, just get the antiderivative and substitute, right? And you have the area instantly. So the second fundamental theorem of calculus, which this video is all about, is a very, very nice one because it allows you to calculate the exact area underneath the curve without doing any kind of approximation. All you need to do is to have the continuous function on this window and just know your antiderivatives. And it's very simple.